These are your notes for Unit 6, Day 5 of Algebra 1. If you would like to see the warm-up, the review question, or any homework questions we covered in class, just look at the finished notes. So today we're going to talk about exponential functions. So this unit we've talked about the rules of exponents, we talked about how to classify polynomials, how to add polynomials, subtract polynomials, multiply and divide polynomials. So today we're going to talk about exponential functions and how to graph them, and then how to use some exponential functions in the real world. So graphing exponential functions. So an exponential function is when you look at the exponent and the exponent is a variable. That makes it an exponential function. So y equals 2 to the x is our first exponential function, because notice the variable is x. So let's just see if we can figure out what this would look like. So if I had 2 to the x, and I'm going to just use my table of values. So if x is 2, we would plug in, if x is 0, we would plug in 0 for x, and we would have 2 to the 0th power. Well, what's 2 to the 0th power? Well, anything to the 0th power is going to be 1. And then plug in 1. 2 to the first power is going to be 2. 2 to the second power is going to be 4. 2 to the third power is going to be 8. But now we're going to go on the other side of the x-axis. What's 2 to the negative 1 power? What happens when you have a negative exponent? Yep, it goes in the denominator. So this would be 1 over 2 to the first, which would just be 2. If you have 2 to the negative 2, that'd be 1 over 2 squared, which would be 1/4. So now let's plot those points on our graph. So we have the point 0, 1, 1, 2, 2, 4, 3, 8, and then we have negative 1, 1/2, and then negative 2, 1/4. So those would be our points. What this graph ends up looking like is kind of like a ramp. So you would start super low, like it's approaching, we're getting really close where x is 0, and then it shoots up to the sky. So I always say that these functions kind of look like ramps. All right, let's look at how this could be different than y equals 3 to the x. So they'll probably look relatively similar, but how do they look different? So let's go ahead and graph that one. So if we had 3 to the 0th power, we would have 1. 3 to the first power would be 3. 3 to the second power is 9. 3 to the third power would be 27. 3 to the negative first power would be 1/3. 3 to the negative 2 would be 1/9. So we still have 0, 1, so they match up at that point. And then you have 1, 3. You have 2, 9. And then you have 3, 27, which would be way up here. And then you have negative 1, 1/3, and then negative 2, 1/9. So it gets lower faster, but it also gets higher faster as well. So that would be 3 to the x. Also looks like a ramp. It's a little bit of a steeper ramp than 2 to the x is. So that is 2 to the x and 3 to the x. All right, let's look at 1/2 to the x and 1/3 to the x. What will these look like? All right, let's start with the first one. 1/2 to the 0th power, well, anything to the 0th power is 1. 1/2 to the first power would be 1/2. 1/2 to the second power would be 1/2 times 1/2, which is 1/4. 1/2 to the third power would be 1/2 times 1/2 times 1/2, which is 1/8. 1/2 to the negative 1 power, well, you would have to flip it, and so it would become 2 over 1. 1/2 to the negative 2 power would be, flip them both, so it would be 2 squared over 1 squared, which would be 4. So we have 0, 1, 1, 1/2, 2, 1/4, 3, 1/8, negative 1, 2, negative 2, 4. So notice this one, and if we went negative 3, it would be 8. So negative 3, 8. It's a ramp, but this time the ramp's going the other direction. All right, let's do 1/3 to the x power. So 1/3 to the 0th power is 1. 1/3 to the first power is 1/3. 1/3 to the second power is 1/9. This would be 1/27th. And then 1/3 to the negative 1, flip it, and you would get 3. 1/3 to the negative 2, flip them, and you would get 9. So we get 0, 1, they match up there, and then you get 1, 1/3, and then, so that gets lower faster, and then negative 1, 3, negative 2, 9, and so it's, again, a steeper ramp. So the 1/2 to the x is the blue graph, and 1/3 to the x is the red graph. So those are exponential functions. So what do you think is going to happen if we transform them or move them? So we have y to the x plus 2 power. So I wonder what's going to happen if we add 2 to the exponent. What do you think that's going to do to the original graph? So if we go back up and look at 2 to the x, 2 to the x looks like that blue graph right there. What's going to happen if we add 2 to the x coordinate? So let's see what happens. So this would be 2 to the 0 plus 2, which would be 2 squared. So this would be 4. 2 to the 1 plus 2 would be 2 to the 3rd, which would be 8. And then 2 to the 2 plus 2, that'd be 2 to the 4th, which would be 16. And 2 to the 3 plus 2, that would be, that would be 2 to the 5th, which is 32. And then if I do negative 1, this would be 2 to the negative 1 plus 2. That'd be 2 to the 1st, which is 2. And 2 to the negative 2 plus 2, that would be 2 to the 0th, which is 1. So we have negative 2, negative 2, 1, negative 1, 2, 0, 4, 1, 8, and then the other ones are too big to graph. So let's do a negative 3. So what happens if I did x is negative 3? So this would be 2 to the negative 3 plus 2. So that'd be 2 to the negative 1, which is 1/2. So it'd be negative 3, 1/2. So now you're going to kind of see it. So it's the ramp, and it looks like this. So how is that different than our normal 2 to the x? Well, that adding 2 is going to shift the whole graph. And which way did it shift it? It shifted it 2 to the left. So it moved that whole graph 2 to the left. So let's look at that graph on Desmos. And I'll show you the difference of those two graphs on Desmos. So if I were to graph both of those on Desmos, so if we had y equals 2 to the x, so that's our ramp right there, and then we have y equals 2, and then we're going to put that in parentheses to the x plus 2. Notice it's that same red graph, but it got shifted 2 to the left. So when we do 2 to the x plus 2, that shifts the entire graph 2 to the left. What if we do y equals 3 to the x plus 2? What do you think adding 2 to the outside is going to do to the graph? So let's try it. So 3 to the 0 plus 2, that would be 1 plus 2, which is 3. 3 to the 1st plus 2, which would be 5. 3 to the 2 plus 2, that'd be 9 plus 2, which is 11. 3 to the 3 plus 2, that'd be 27 plus 2, which is 29. 3 to the negative 1 plus 2, that would be 1/3 plus 2, so that'd be 2 1/3. 3 to the negative 2 plus 2, that would be 1/9 plus 2, so that'd be 2 1/9. So if I graph this, I get 0, 3. I get 1, 5. I get 2, 11. I get 3, 29, so that's outside of my graph. I get negative 1, 2 1/3, and then 2 1/9. So this graph is gonna, it's gonna look like that purple graph. So notice, how does that look different than the normal 3 to the x? Well, that 2 is gonna shift the entire graph up 2. So it's 2 up from where it was originally. So let's graph both of those on Desmos. So y equals 3 to the x, and y equals 3 to the x, and then plus 2. So notice the green graph is the original 3 to the x, and y equals 3 to the x plus 2 shifts that entire graph up 2. All right? So why don't you guys take a minute and try and graph both of these. Y equals 2 to the x minus 1 and y equals 3 all raised to the x minus 1 power. And when you're done, you can check your work against Desmos or against our finished notes from class today. So go ahead and pause the video and try. All right, so some real uses of of exponential functions in the real world. Well, one is the compound interest formula. So the compound interest formula is used in banking, and it's when you want to invest money into a savings account or into bonds or things like that. You earn something which is called an interest rate. So it's how much money your investment. So if you put money in a savings account and it has like 3.7% interest, that's how much interest or extra money you earn per year on that account. So the compound interest formula looks like A, and A is going to be your final amount. So it's the final amount of money that would be in the account. P is called the principal, and it's the original amount of money that you invest. So it's the original amount of money that you're going to invest. So if you put $500 in the bank, that's your principal, or that's the original amount of money you're going to invest. R is your interest rate, and you're going to write it as a decimal. So if it's like 5% interest, 5% as a decimal would be 0.05. N is how many times it's compounded per year. So that means how many times that interest is taken per year. So let's just say you had like an account that earns 12% interest and it's compounded monthly. That means that you get part of that interest every month. So if it's 12% interest and you earn a little bit every month, you would take 12% divided by the 12 months. And that means that you're going to earn 1% interest every month on the account. So N is the number of times your investment is compounded per year. So that's going to be your N. And so both of those are N's. And then the T is going to be the number of years. So that's what all of those different variables mean in this problem. So A is going to be the final amount of money that you would have in your account. P is the principal, or the original amount of money that you invest. R is the interest rate. We're going to write that as a decimal. N is the number of times that your money is compounded per year, the amount that interest is compounded per year. And then T is going to be the number of years that your money is in that account for. So let's look at an example. Find the amount owed at the end of 8 years if 15% is loaned at a rate of 6% compounded monthly. So you can also do this the reverse way. And if you took out a loan, then the final amount would be how much money you owe instead of how much money would be in your account. So 15% is the original amount. So that is your P. 6% is the interest rate. So that's the R. And 6% as a decimal is 0.06. Compounded monthly, that means that every month it's compounded. So N would be 12. So now our formula is we don't know the final amount. The original amount is $15,000. And then it's 1 plus the interest rate, which is 0.06, divided by N, which is 12, and then raised to the NT power. And since it's 8 years, T is going to be 8. So 12 times 8. So that's our problem. So now what we do on a normal calculator, we follow the order of operations. So we've got to do the inside of parentheses first. So we are going to do 0.06, because we do divide before we do anything else. So 0.06 divided by 12, and you get 0.005. So we get A equals 15,000 times 1 plus 0.005 raised to the 12 times 8 power. And now order of operations says keep doing the inside of the parentheses. So we're going to add 1. So now we get 15,000 times 1.005 raised to the 12 times 8 power. So let's figure out our exponent. 12 times 8 is 96. So I'm going to change that exponent to 96. So now order of operations says we need to do exponents next. So we're going to do 1.005 raised to the 96th power. And we get A equals And we don't want to round on that because we want to be as accurate as possible. So 15,000 times 1.614, and then we'll just do 1427. And then we're going to multiply that by 15,000. And we get the amount of money that you will owe after 8 years if you borrow $15,000 and the rate on that loan is 6%, you will owe $24,212.14 at the end of 8 years. So you owe $9,000 extra dollars at the end of those 8 years. And that is a real-world application of an exponential function. So let's look at another example. Find the amount owed at the end of 8 years if $12,000 is loaned at a rate of 9% compounded semi-annually. So we have A equals P, 1 plus R over N to the NT power. So the original amount of money invested is $12,000. So P is going to be $12,000. And then it's going to be 1 plus the interest rate is 9% as a decimal. That's 0.09. So 0.09. Compounded semi-annually. Semi-annually means twice, so it's compounded twice a year. And then 2 times 8 years again, so 2 times 8. All right, order of operations says do the inside of parentheses first. So we're going to do the inside of those parentheses first. And we do 0.09 divided by 2. And so we get 0.045. We'll add 1. And so we get A equals 12,000 times 1.045 raised to the 2 times 8 power. That would be 16. So I'm going to do 1.045 raised to the 16th power. And we get 2.0223. And then once you're done with that, we're going to multiply it by 12,000. And so the amount of money that you would owe after 8 years would be $24,268.44. So you owe over twice the amount of money that you borrowed at the end of 8 years if it's 9% interest. All right, let's see us gaining some money now. So you deposit $5,000 into a savings account that earns 1.2% interest compounded 3 times per year. How much money do you have in your account after 15 years? Okay, so A equals P, and then 1 plus R over N to the NT. So we're starting out with $5,000, so that's our P, and then 1 plus the interest rate is 1.2%, so as a decimal that's 0.012, so 0.012 over compounded 3 times per year, so N is 3, and then raised to the 3 times how many years have gone by? 15 years. All right, so let's do some calculations. So we're going to do inside of the parentheses, divide first, so 0.012 divided by 3, and then add 1. So we get A equals 5,000 times 1.004 raised to the 45th power, because 3 times 15 is 45. So 1.004 raised to the 45th power, and then we're going to multiply that by 5,000. And we now have, at the end of 15 years, we have $5,983.94 if we round up. So we started with $5,000, and at the end of 15 years, if it's earning 1.2% interest compounded 3 times a year, you would end up with $983 extra at that point. Make sure all our calculations were right. 0.012 divided by 3 plus 1, 1.004 raised to the 45th power times 5,000. Yep. Okay. So that is the compound interest formula. You also have something called simple interest, and I think this is probably what you guys have worked with in the past. So it's basically the same formula if you want to look at it. You can say A equals P, and then it's going to be 1 plus R to the T, or A equals P, and then 1 minus R to the T. I think your book uses different formulas. You can use the same formulas if you want to. So A is going to be the final amount. P is what you originally invest. I think in the book they're going to let C be the original investment. They'll let X be the number of years And then R is going to be the rate. And again, you have to write it as a decimal. So if you are gaining, you would add. If you are losing, you would subtract in the rate. So in 2018, the population of the city of Seattle was 745,000. If the population is growing, so that means we're growing, so that's we're going to add the rate, at a rate of 2.1% per year, what will the population be in 2025? All right, so the original population, or the starting population of Seattle, would be 745,000. And then it's going to be 1 plus the interest rate written as a decimal. So 2.1% written as a decimal would be 0.021. And then raised to the number of years. Well, we're starting in 2018 and we're going all the way to 2025. So how many years have gone by between 2018 and 2025? 7 years. And so now we just get to calculate that. So order of operations says start on the inside of the parentheses. So 1 plus 0.021, you get 1.021. So the final population of Seattle, we're going to do 1.021 and then raise to the 7th. So 1.021 raised to the 7th power. And then we're going to multiply that by 7. And we get 861,661, and we won't write it as a decimal because this is the number of people. So that would be the population of Seattle in 2025, or the estimated population of Seattle in 2025. All right, let's look at another one. The number of students in a in summer school at a local college has been decreasing, so that means we're going to subtract the rate each year by 5%. If 2,024 students currently attend summer school, predict how many will attend in 12 years. So the final amount will equal the original amount, and then it's going to be 1 minus R this time because it's decreasing, and then raised to the number of years. So currently there's 2,024 students, and then 1 minus the rate. Well, the rate is 5%, so 0.05. And then we want to know after 12 years, how many students would you predict to have in the summer school program? So we are going to do 1 minus 0.05. And we get 0.95. So A equals 2024 times 0.95 raised to the 12th power. So 0.95 raised to the 12th power. And then times 2024. And then in 12 years, they should expect to have about 1,093, 94 if you round up. So we'll take 1,093 students should be enrolled in the program in 12 years. A form of uranium has a half-life of 62 years. How much of a 100-gram sample is present after 500 years? So half-life means that each time it goes down, or like in 62 years, there's half of the original thing present. So if you started with 100%, basically what you're saying is the rate is, it's going down by 50%. So you can say that it's decreasing at a rate of 50%. So A is going to equal P times 1 minus the rate, and then raised to, we want 500 years, so we can just call that T. So we're going to do, we want how much is going to be left after 500 years. So we're going to start with 100 grams, and then it's going to be 1 minus 0.5 for 50%. And then after 500 years, we want to know how many times it's half-life. So in T this time is going to be the number of times it's half-lived. Okay, well, 500 years, how many times has it half-lived? Well, it takes 62 years for it to half-life. So we're going to take 500 divided by 62, and that's going to be how many times the half-life has happened. So we're going to take 500 divided by 62, and the number of times that it's half-lived is 8.0645. So that is going to be our T in this case. So 8.0645, because that's the number of times that it's half-lived. So we're going to take 1 minus 0.5. So we're going to take 0.5 raised to the 8.0645. And then we're going to times that by 100. And so the amount of uranium that would be left if you started with 100 grams, the amount that would be left after 500 years would be 0.3735 grams. So a little bit of a different problem. So those are just some examples of how exponential functions can be used in the real world. And I just want to go back up to this one and make sure that I put all of that math in right. And we got 1.004 raised to the 45th power, and then times 5,000. Yep, okay, everything looks good. That just seemed like too little amount of money.